Okay, good afternoon, everybody. How was your weekend? I hope you had a good one. Though I understand that you still have a lot of work to do as far as Cal 2 is concerned. So I hope you had enough rest and you are now ready to go back to to this to academic shape for Cal 2. So I was told that today you finished Arclengths surface areas and centroids in the lecture. So we'll be ready to answer some examples on that. So for that, I prepared worksheet number 4. A blank version is already available on my website. But basically, this is just the problems from the textbook. So I just took the problems from the textbook about arc lengths, surface areas, and centroids, essentially section 7.5, and then put it into a PDF which we can annotate. So the odd numbered problems here have final answers that are available in the textbook, so you can take a look at them. So perhaps what we'll do is try some even numbered examples, or if you find some of the odd numbered problems interesting, then we can also take a look at them. But before that, I see there's a question sent by Madison in the chat. So if you still have some, because I think Arclengths, which is my target for today, is a pretty straightforward topic. So I guess we can devote the first half, perhaps, of today's meeting to answering any problems that you might still have about computing volumes using the method of disk core washers and cylindrical shells. So just send them in the chat if you have some questions. And with that, I'll start with Madison's question, which is a good one, actually. I guess this is part of your e-homework. So problem 19, which might look very intimidating. So in problem 19, I'll just label it problem A in my notes, but this is problem 19, I guess, from some of your homeworks. So it says that you have a region R in the first quadrant that is bounded by the function f of x equals cx squared and y equals 2. And when r is rotated about the axis of revolution y equals, the axis of revolution here is the x-axis, or the equation of the y-axis is y equals 0, then the volume of the solid is known to be 64 pi over 5. And then what we need to look for is the value of c. Okay, so this problem is different from what we considered last time, because before we are given the functions explicitly. We know the axis of revolution, and then we solve for the volume, or at least we set up the integral that gives us the volume, and from there, we're done. But in this particular problem, it's sort of the reverse, wherein we know the volume, but we don't know exactly what the function or how the function looks like, right? So the only info about the function that we have is that it is of the form cx squared, where we want to find the value of c. Well, let's see how to do it. Well, c is an unknown constant, so let's just deal with that. Just imagine c to be a parameter, or it is a constant. We just don't know its exact value yet. So with that in mind, cx squared is the equation of a parabola, right? Whatever the value of c is. The effect of the value of c actually is on the opening of the parabola, because if c is positive, it opens upward. If c is negative, then it is opening downwards. And c also determines the width of the parabola, or how long is the opening of the parabola. So, but basically, it's a parabola opening up or down. But another clue from the problem is that we will be dealing with a region in the first quadrant and bounded y equals 2. So that means it will not make sense if the parabola is opening downward. Because if the parabola is opening downward, then there would be portions of the region that will be in the fourth quadrant. So I'm imagining here the problem's intention is to let us know that the parabola is opening upward so that we will have a well-constructed region on the first quadrant. So here, assuming that C is positive, then the parabola will open like this. Okay, because otherwise, again, it will be opening downward, and then it will not give us a region purely in the first quadrant. Okay, and then the other boundaries, y equals 2. So here, let's have y equals 2. And then we are just concerned with the region in the first quadrant. So this would be the region R. And this region R would be revolve about the x-axis. Okay? Right. So that means we need to find the volume. But one thing about the volume is we know that the exact value of the volume is 64 pi over 5. But let's start by setting the integral that will give us the volume. Well, you can do either cylindrical shells or disc or washer, depending on what type of strip you want to use. But for this particular example, I will be what? I will be taking advantage of the fact that the function is given in terms of the variable x. So I will use x here as my variable. But again, nothing is preventing you from doing dy, but that will require you to solve for x in terms of y. So I'll stick with x. And then the bounds for this integral would be the starting x and the ending x value for the region. Well, we know that the region starts here, but that's at x equals 0. So that's the lower bound. And the region will end here. But here we have some x value, right? So we need to find what that x value is, because that would be the upper bound. Well, that x value is the x component of the point of intersection, because that is where the parabola meets the line. So that means we need to find the POI by putting the two equations equal to each other. So I have cx squared equals 2. And solve for x. Now c is an undetermined constant. I know this is greater than 0, so I can divide both sides by c, having 2 over c. And then I will take the square root of both sides. So we get x equals plus or minus root of 2 over c. But again, we are on the first quadrant, so our only choice is x equals the positive root of 2 over c. So here we'll have 2 over c as our upper bound, which is perfectly fine because here we are assuming that c is any constant, or is just some constant. Okay? All right. And then what would be the integrand? Since here I resolved on using x, that means I'll be using vertical strips. And vertical strips are perpendicular to the axis of revolution. So here we will use the disc or the washer method, right? But if you draw a line from the AOR, or if you'll draw a strip from the AOR towards the end of the region, you will see that some portion of that strip will be outside of the shaded region. So that means here I know it would be a washer problem. Okay, the cross sections are washers. So whenever the cross sections are washers, then what will happen is that we'll have a pi outer radius squared minus inner radius squared. So I'll have outer radius squared minus inner radius squared. So we need to determine what are these radii. Okay. Now outer radius first. The outer radius will be just this. And how long is this radius? Well, it's a vertical strip, so do top minus bottom. The top is y equals 2. The bottom is y equals 0. 2 minus 0, that's going to be 2 units. So the outer radius is 2 units. Okay? Now, you could have done that without doing top minus bottom, because from the figure, you know that the outer radius will always be 2 units, okay? But you can also go back to basics and do top minus bottom. Now for the For the inner radius would be basically how long is that strip, how long is the portion of the strip that goes out of the region. So here, this would be my inner radius, okay? And again, that would be top minus bottom. Top function is the parabola. I know the equation is cx squared. The bottom function is y equals 0, so minus 0, I'll still have cx squared, okay? So that is the integral that gives us the volume of the solid. But the problem tells us, oh, the volume would be 64 pi over 5. And actually our goal is to find the value of the constant c. Well, all you need to do here is to evaluate this integral up, okay? Now, if you do that, let's just simplify a bit. This would be 4 minus c squared x to the 4th dx, okay, equals 64 pi over 5, okay? And I guess now it would be straightforward. All you need to do is step 1, find the antiderivative, and then plug in the upper bound, the lower bound, and then subtract them from each other. So you'll eventually end up here with an expression involving c, okay? And what is that expression? That expression is the one you get after evaluating this integral, okay? There would be c's in there because z is a constant, so you integrate, find the antiderivative, plug the upper bound, plug the lower bound, simplify things, you'll have an expression involving c. Put that equal to 64 pi over 5, and then solve for c, then you'll get the desired value, okay? So I'll leave the evaluation to you guys, but I hope the setup is clear. Okay, sure. Yeah, this types of problem looks very intimidating. So I suggest you try to read them line by line, phrase by phrase to see how those things are looking up. Okay. Okay. So I see that Christina, you figure out what you had been doing wrong with this problem. So I guess you don't need help on that anymore. So if so, I'll go to okay. So I think you got it, Christina. So I'll go to Robert's question. Translate the equation in 18 in terms of y. Let me see. Okay. So this is Robert's question. But first, Christina, do you still need help with that problem? I see that Robert already helped you on that. So let me know if you still have question. But while waiting for that, I'll go to Robert's question. Robert is asking for help solving for y, translating the equation in terms of y. Okay, yeah, let me see. What's the equation? Okay, so for this problem, the equation is y equals negative x squared plus 2x. So I suppose that here for problem 18, you're just required to find the volume of the solid, and you could have done that by just integrating with respect to x. But if you want to check your answer, it will also be good to set it up using the variable y. So I take that that is the reason why you want to translate this equation in terms of y. So let's try to do that. Well, the thing here is we want to solve for x in terms of y, all right? But the thing here is x is involved in both the quadratic and the linear terms. So what you will do here is to do completing the square. Okay, so basically what you want to do here is to make sure that x squared will have coefficient 1, so that this entire formula or this process that I will describe will work. Okay, now that's what our first problem here, that x squared has a coefficient -1. So to force that it has a coefficient 1, I'll divide both sides by -1. So I'll have negative y equals x squared minus 2x, right? I only did that for the sake of the next step. Because if the coefficient of x squared is equal to 1, then the completing term will simply the square of half of the middle term. So look at the middle term. The middle term is -2. Take half of it, so you get -1. Square -1, that's your completing term. So half of it is take half, then square. So half is -1, -1 squared is 1. That's why I knew I needed to add 1 to both sides. Okay? And the reason why I want to complete the square is so that I can factor the right-hand side. The right-hand side now can be factored as x minus 1 quantity squared as a perfect square trinomial, and hence the term completing the square. Okay? And then now I can take the square root of both sides. So taking the square root of both sides, the square will be gone on the left, on the right side. On the left, I'll just rewrite it as 1 minus y, and then take the square root, take the positive and the negative root. And then finally, if you want to solve for x in terms of y, you will get x equals 1 plus or minus root of 1 minus y. Okay? And so here you will see that the right half of your graph or of the parabola will have 1 plus square root of 1 minus y, and the lower half would be, or will it be the lower half? No, the left half would be 1 minus root of 1 minus y. Okay? Does that make sense, Robert? Okay, great. Any other question before we proceed to Arclengths? Okay, none? Good. Now let's try Arclengths. I guess of all the applications for integrals, setting up the integral that gives us the arc length, I guess is the most straightforward of them all, because this will just have a very straightforward formula. And I hope the reason, or I suppose the reason why this formula works is already tackled in the lecture. So I'll skip those technical details, and let's just accept the fact that the arc length is just the integral of from a to b of the square root of 1 plus the derivative of the function squared dx. So here, this formula will work as long as your function is continuous over the interval ab. Okay. So that formula L for L gives us the arc length of a continuous function f over the interval ab. So all you need to do here is to compute f prime, take its square, plug it into the formula, and integrate from a to b, and that's it. That's straightforward. Well, if you want to, if the function is given in terms of y, then the formula is analogous. It will just be the integral from c to d of the square root of 1 plus g prime of y quantity squared dy. Okay, so it depends on how the function is given. So if you, oh, by the way, I forgot if I already mentioned this, but I already uploaded worksheet number 4 in my website, which is basically the compilation of exercises at the end of the textbook for section 7.5. So I'll pick some of the items there. Let's see. Okay, perhaps let's try problem 10. Or you can suggest what problem number you want to discuss, but yeah. Let's try problem 10. For problem 10, the function is h of x equals ln of cosine x over the interval pi over 6 to pi over 3. Okay. And the instruction here is to find the arc length. So we need to compute the arc length. So we will not just stop at finding the integral in setting up the integral, but we need to evaluate that integral. So that's one thing. You need to be careful about what the problem is asking for. Is it asking for the actual arc length, or is it just asking for the integral that will give us the arc length? Because sometimes you don't need to evaluate the integral, sometimes you do, right? So make sure you read the instructions carefully. Oh, that reminds me that we started grading the written homework you submitted last week. Our deadline to finish it is at the end of the week. So expect to get it over the weekend or early next week. Um, there are 10 problems in the written homework. Problems, the odd numbered problems, 1, 3, 5, 7, and 9, are all graded only for completion. So that means if you have a complete attempt at that problem, you get the 5 points. 5 points for each of them. So a total of 25 points if you have a complete attempt. Now, the even numbered problems, 2, 4, 6, 8, and 10, are graded for accuracy, and they are worth 15 points each. So only for the even numbered problems will we go into the details looking into your solution. You get partial credits if you didn't get the entire solution properly, but it would be worth 15 points. For those graded for completion, if you did not finish if you didn't finish the attempt to the solution, then you get 0. Okay, so basically those graded for completion are just either 0 or 5. For those graded for accuracy, it's 0 to 15. We can give partial credits. Oh, Robert, I'm pertaining to the written homework that you uploaded last week in the in CASA, the written homework. It's just that the grader, the TAs are grading it. So yeah. Yeah, that's the written homework you submitted. There is no separate requirements for this class. So, but we are the ones grading your tests and your written homeworks. Okay, and just as a disclaimer, I might not be the one who will be grading your work, your homework, because the homeworks are distributed randomly to all TAs teaching calculus 2. So I got my share. I am supposed to grade 98 papers, I guess, or 96 papers, and they are not necessarily the ones from you guys. So yeah. But if you have some questions about how was your homework was graded, if you think you should have gotten more partial credits for a particular item, then you can let me know when you receive it. We usually give you 3 to 5 days to take a look at the homework and see if the grading was good. If you have complaints or questions about the grading, just let me know. I'll review it. Even though I'm not the one who graded it, I'll take a look at it and I'll make recommendations whether to give you more points or not. Okay. Now, going back to business, problem 10, we need to find the arc length. So let's see. Yeah, Madison, you're referring to the number of papers I need to grade. Yeah, that's a lot. That's why we need a week to finish grading it. Okay. But anyway, going back here, we need to find the arc length. So, but remember, for the arc length formula, we need the derivative. So we need to find the derivative of h. So I hope you still remember how to take the derivative. So it's ln of something, its derivative is 1 over the something times the derivative of the something, because chain rule will kick in. So derivative of cosine is negative sine x. And this would be what? This would be negative tangent x. Okay. And note that h prime quantity squared is just secant squared x. Okay. So that's straightforward calculations.
I thought negative tangent x was already the derivative.
Yes, that's the derivative of h.
Okay, so 1
sorry,
minus.
yeah. Mm-hmm.
Or 1
I'm
plus
thinking ahead, yeah.
Okay. I was like, that's where I was. I was just wondering.
Yeah. Sorry about that. I was thinking ahead because when I plug it into the formula, yeah. Thank you for that. So, okay, so that's tangent squared x. And then I'll put it inside the formula for the arc length. So I'll have the integral. I know the interval AB. So I'll have pi over 6 until pi over 3 of the square root of 1 plus derivative squared, okay, dx. And then I guess this is where I was thinking the secant squared here because here the radicand 1 plus tangent squared is just secant squared x dx using trig identities. Okay, that's why I'm thinking secant squared earlier. But anyway, so here we'll have pi over 6 until pi over 3 of secant x dx. Okay, is that good? Okay, and now we integrate secant x. I guess we have a formula for the integral of secant x. So you can go back to your calculus 1 notes. The integral of secant x is the ln of the absolute value of secant x minus tangent x. And then we need to evaluate that. Sorry, it's a plus secant x. Yeah, plus tangent x. And we need to evaluate it from pi over 6 to pi over 3. Okay. All good? Or should have I started with a much easier problem? Well, this would be a good review of of these things from calculus 1. Okay, and then let's see. So we need to evaluate the integral. So I'll first plug in the upper bound minus I'll plug in the lower bound. And here we need our unit circles. So let's see, what is secant of pi over 3? You guys still remember? So this tells us we need to review all these things from algebra. So this would be ln of secant of pi over 3 is equal to 2 plus tangent of pi over 3 is, let me see, so that would be sine over cosine. So that would be root 3 minus ln of the absolute value of secant pi over 6. That would be 2 root 3 over 3 plus tangent of pi over 6. But tangent of pi over 6 is just root of 3. Oh, sorry. Tangent of pi over 6. Yeah, that's root of 3. Root of 3 over 3, rather. Yeah. 1 over root 3. Hold on. Yeah, root 3 over 3. Okay. And we can leave the final answer like this. Yeah, this is one thing I noticed in the homeworks. Students always still try to find the numeric value for this, guys, and they end up using calculators. But yeah, it is preferable to keep it in its exact form like this rather than using calculators to find a numeric value. Because in the exams anyway, you are not allowed to use calculators, at least as far as I know. So you are not expected to get a decimal value for this. So this is perfectly fine as your final answer. Or at most, you can just say, oh yeah, you can leave it like this. Yeah, I won't give the another simplified version. All right. Good, guys? Okay, good to know. Uh-huh. Or you might be bored because this topic is very easy. Problem
I'm
18.
screaming right now, so yeah. See, yeah, exactly what Curtis said. 18 on the homework, like, it scares me.
Problem 18 in the homework. So, can you send?
Homework. Maybe he's talking about the worksheet. I don't know. I'm just scared.
Yeah, let me see. Is that the worksheet? Yeah, let me see what problem 18 is. Is that scary? Hold on, I lost my copy. Where's my copy? There. Problem 18. Yeah, I didn't go ahead and solve this prior to the class, so I just copy pasted it from the textbook. But okay, I see. That really looks intimidating. So for problem 18, we need to find the arc length of x equals beta y minus 4 over 9 beta squared raised to the 3 halves over the interval AB. Well, I understand why you guys are scared about this because you see a lot of Greek letters, so it's usually terrifying if you see math being combined with not just the English alphabet, but with these Greek letters in it. But if you look closer, you'll just realize, okay, this is x, so this must be a function of y, because either y equals f of x or x equals g of y. So basically, this guy, this scary guy over here, is a function of y. So all other letters that I see in here should be treated as constants. So that tells me only y's are variable. So here, the betas are or is a constant. And it will be treated as such as we go along in our solution. The same thing goes for the bounds, because here we are not given the exact bounds or values for a and b. We're just told that the bounds are a and b. Again, these are constants, so let's just treat them as constants, all right? So if you want to get the arc length, remember we need to find g prime. Because the derivative is squared, and then we need to put it inside a formula for the arc length. So let's look for g prime first. So g prime is the derivative of something to the 3 halves. So I'll need to apply the power rule, then the chain rule. So I'll have 3 halves times beta y minus 4 over 9 beta squared raised to the 1/2, and then chain rule kicks in. I need to multiply it by the derivative of the inside function, which is this guy. The derivative of the expression in red is just beta. Right? Do you see that that is just beta? Because the derivative of beta y is beta, because beta is a constant. And then 4 over 9 beta squared is also a constant, because beta is a constant. So the derivative is 0. So this is basically our g prime. And then if we square this, or you can just write it first as a 3 beta over 2 times the square root of beta y minus 4 over 9 beta squared. And then remember, for the formula for the arc length, we need the derivative squared. So we need to square g prime. So if I square g prime, it would be 9 beta over 4 times beta y minus 4 over 9 beta squared. And then I can distribute the scalar multiplier inside the difference. So this would be 9 beta squared y over 4 minus 4 cancels, 9 cancels, one of the betas will be canceled. This would be 1 over beta. Okay, is that good? Oh, sorry, this is beta squared. Remember, I am squaring beta, so this would be beta to the 3rd. And then this would be gone. This would be 1. Okay. Yeah, I hope that is correct. So please pay extra attention to my arithmetic or to my algebra, Sometimes I mess those easy things up. So I guess this is correct. So now we're ready for the arc length. The arc length is the integral over the interval. The interval given is a to b. We were not told what the exact values of a and b are, so let's just keep it a and b. Inside the integral will be the square root of 1 plus g prime squared. We already knew what g prime squared is, so I'll just copy this over. Oops. Just have that there. Get a little smaller. There we go. And then dy. Okay. And then simplify. I'll have integral from a to b of the square root of 9 beta cubed y over 4 dy. I can simplify further as the integral from a to b of 3 halves beta to the 3 halves y to the 1 half dy. Okay, and then remember beta is a constant. 3 over 2 is a constant, so we can write it more explicitly as this. I'll take the scalars out of y to the 1 half dy. Okay, and then now I can integrate. So this is 3 over 2 beta to the 3 halves times y to the 3 halves evaluated from a to b over 2/3, over 3 halves rather. Okay, so I integrated y to the 1 half. It's y to the 3 halves all over 3 halves, but I can cancel this and this. So we'll just have beta to the 3 halves times y to the 3 halves evaluated from a to b. A and b are just constants that we don't know the exact values of. So, but basically this will be beta to the 3 halves times b to the 3 halves minus a to the 3 halves. And that's it. That's the arc length. And this qualifies as a final answer is because we don't have the variable y anymore, right? Beta is a constant. A and b are constants. We just don't know their exact values. So we can stop here. All right. So you see, it's not that bad at all. It's just that you need to break down that intimidating problem into pieces. Just realize that betas are constants. We just don't know their exact values. A and B are constants again, and they should be treated as constants all throughout our solution. Okay? Any other problem in this? None? Okay. Now, yeah, Brian, problem 17 would be similar. So for problem 17, I'll set the integral up and I'll leave the evaluation to you. So for problem 17, the function is x equals 2y minus 1/9 raised to the 3 halves. And y is between 1 and 4. Okay, actually, this is much easier than 18. But anyway, okay. Now this is g of y because you have either y equals f of x or x equals g of y, but the process and the formulas are similar. So here I need first to solve for g prime of y. So the challenge here is to make sure you remember how to differentiate. Okay, so you go back to Cal 1. You need to apply the chain rule, the product rule, the quotient rules, and all of the rules we learned there. So here, if we look for g prime, it's going to be 3 halves, 2y minus 1 over 9 raised to the 1 half times the derivative of the inside. Again, this is the chain rule. Okay. So the derivative of the inside is just 2. So this simplifies to what? This simplifies to 3 square root of 2y minus 1/9. Okay. And then if we look for g prime of y squared, we simply square the derivative, so it's going to be 9 times 2y minus 1 over 9. Don't forget that the scalar multiplier also gets squared. Okay. And then we can simplify this as 18y minus 1. Okay. And so now we're ready to plug this info into the formula for the arc length. So the arc length would be an integral from 1 to 4, because that's the given interval in the problem. And then square root of 1 plus the derivative squared. We know that the derivative squared is 18y minus 1 dy. And then you simplify. So this would be root of 18y dy. And then I guess you can integrate it easily. So I'll just leave the integration to you guys. Okay. Right, is that okay? Okay, any more question about this? Does computing the arc length make sense? Do you foresee any difficulty on this? What I see as the major difficulty here is finding the derivative. So you should be careful and make sure that you still remember how to compute the derivatives properly. Okay? Any other requests from the worksheet? Of course, as always, I just uploaded the worksheet today, so you can try some problems from there later today, or if you have free times also tomorrow. And then let me know on Wednesday if you find some problems difficult there. Okay, and then we can discuss them together. All right. So honestly, I haven't solved those problems yet, and I do not intend to upload a completed solution to worksheet 4. Okay, because this is quite long. So you just let me know what problems you think are problematic. Again, the answers to the odd numbers here are in the textbook, so you can take a look at the final answers there. So, but for the even numbers, you can work them out if you have some difficulties with them. All right. So if there are no more questions, then probably we can also jump into surface areas, because I guess that's the next application here. And this is very related to arc lengths. Because remember, surface areas is just the measure of the outside face of a three-dimensional object. So for instance, if you have a cylinder, this, yeah, the surface area is just the amount of material that is needed to construct the boundary. I still ended up shading everything, but that is just okay. So that is just we are measuring the outside or the lateral place, the lateral face of the three-dimensional solid. So we don't care about what happens in the inside of the solid or in the interior, but just the outside face of the solid. So basically, we want to compute that. So let's use integrals for it. Yeah, it's fine, Robert. So sometimes I'm just looking at your meme, and part of me is trying to react to it, and part of me is trying to complete my sentences. But anyway, okay, let's see how this is done via integrals. So, okay, let me cut this. Right. So the idea here is instead of a region, we will revolving just an arc over an axis of revolution. So if you have, say, this arc from A to B, okay, and then say we revolve it around, say, some axis here. So say this is our AOR. So remember what happened when we have a shaded region. If we have a shaded region and we do the revolution, then what happens is we produce a solid, something that has a material in the inside, okay? But this is a different case because what we are revolving around the axis of revolution is simply a curve, is simply an arc. So I hope you can imagine what will happen here after the revolution. All that will happen would be, hold on. Okay, what will happen here is we will be getting a three-dimensional object, but one that is hollow inside. Do you agree? I hope you can imagine what will happen because when we had the shaded regions that are rotated, we are producing solids with materials inside. But if you will simply rotate this arc, you'll get a 3D object that is hollow inside, or there would be purely empty space in the inside, right? So basically what you'll produce is something like this for every cross section, right? So if you do the revolution that way. So that's why we are only computing surface areas, because this won't have a volume, because the inside would be empty space, okay? Now, how do we compute the surface area? Well, the surface area, I'm not sure what is the variable you use for the surface area in the lecture. Did you use S or A? I'm used to using SA for the surface area, but anyway, they are just notations. So I'll call the surface area SA for now. This will still be an integral, but now this is an integral from A to B. Where does A and B, where do A and B come from? They are the bounds for the arc length. So the arc started at x equals A and ended up at x equals B. So that's why I have those bounds. And then what we'll have here is 2 pi r times the arc length, or not exactly the arc length, but the integrand in the arc length. So this would be a square root of 1 plus, let's say this is y equals f of x, f prime of x quantity squared. And let's see why we have these factors inside the integral. Well, basically, the surface area will certainly depend on how long is the arc, right? It will sort of say it will serve sort of as the height for your surface of revolution, and that's why we got the arc length inside the integral. All right. And then why do we have a 2 pi r? We will have a 2 pi r because remember this region is being rotated with respect to the axis of revolution. So therefore, that arc length or that arc travels along a circle, right? And we will simply sum up all of those arc lengths all over those circles. And there would be infinitely many of them. That's why we are integrating. And to find how much is this, right? Or what is that distance? That will basically be the circumference of this circle. Or you can interpret it as the distance traveled by the arc. So basically, it will travel along the circumference of the circle. That's why you have a 2 pi r there. That's the formula for the circumference. So 2 pi is a constant. That's fine. Put that into your formula right away. The only challenge here is finding r. And I guess that is Robert's question. What is the r? Well, the r is the distance between the function and the axis of revolution. Okay, yeah, you're right, and the axis of revolution. So r is pretty much this distance. How far is the arc from the axis of revolution? Sorry. And for that, if your solid of revolution looks like this, then it will be top minus bottom. F of x minus the y value at your cross section. Because what you want to measure is how far is your arc from the axis of revolution. This is the thing. I was browsing through the textbook earlier, and it looks like that you are only considering surfaces of revolution that has the coordinate axis as AORs. Is that also the case in the lecture? I mean, you are looking for the surface area of the surface form by revolving an arc about, say, the x-axis or about the y-axis. I'm thinking you did not consider revolving your arc with respect to, say, x equals 2, y equals -1, and so on. Or you're not sure. But anyway, that's the general formula for the radius r in this formula. That is the distance between the arc and the axis of revolution. So you do top minus bottom or right minus left. In the examples in the textbook, the axis of revolution are always the x-axis or the y-axis. That's why you subtract 0 from the function because they are easy. But if the axis of revolution happens to move up or down the y-axis or left and right on the x-axis, then you should do right minus left or top minus bottom. Okay? Now, we don't have, it's already 10 minutes before 1. So I guess let's start solving surface area problems next meeting. Let's call it a day here, unless you have some clarificatory questions. I hope everything's clear, at least finding the arc length. And then on Wednesday, I guess we'll start with examples for surface areas and centers of mass or centroids, all right? Okay, no questions, everybody? Anyone? Okay, so let's call it a day. Thank you for coming today and enjoy the rest of your day. See you on Wednesday. Goodbye, everybody.